We can use the kinematic equations to determine when two objects will collide with each other. All we need to do is to set the frame of reference to the first object and let the math take care of the rest. Let's go through an example. All right, let's say we have these two rugby players. We'll call them Adrian and Bobby. There they are, all right, and they're running in opposite directions. Adrian is accelerating towards Bobby, and Bobby is traveling at a constant velocity back towards Adrian. And the question is, when will they end up colliding with each other, creating a big wha-pow? Okay, so we'll start by solving this problem graphically, all right, so they can follow along with me visually at home, and then we'll back it up with the mathematics. All right, so for Adrienne, it's a quadratic correlation because she's accelerating from rest, and Bobby is moving at a constant velocity but in the opposite direction, so we'd expect him to have a negative slope on this graph. Another thing about the story here is that they are 37 meters apart. So we know that Bobby, he will start at 37 meters in front of Adrienne. All right, so this is the frame of reference of Adrienne, and everything will be calculated from her frame of reference. All right, so he'll be traveling backwards like so. And if we combine both of these graphs together, we can find the point of intercept, and that is when they will collide with each other. All right, so from this graph over here, we can determine that at around 7.5 seconds, that's when they'll bump into each other. We can also figure out at what position they'll bump into each other. All right, so 14 meters ahead for Adrienne, and as for Bobby, it would be, I guess, 37 subtract 14. All right, and that's at what position will they bump into each other. I guess the question didn't ask for that, but that's how you'd calculate it out. How fast was the accelerating player going? Now, if you're going to take the old school approach that we covered a few days ago, which is by drawing a tangent, here's the line that touches the curve once and only once at the point of intercept is what we are interested in. And as from before, you'll want to choose 2 points on the graph. Do I have it animated out? Oh yes, I do. All right, that more or less pass through the crosshairs. It may not be perfect, but anything that's super close to the naked eye is sufficient enough. All right, because again, if you do a small tangent, your errors are going to be rather large. All right, but if you draw a big tangent, as you're dealing with your delta, because slope is equal to delta y over delta x. If your delta y is a big difference, for example, 283 subtract 28, then at least you'll have a 3 significant answer over there to do your calculations with, as opposed to 2 subtract 1, which will give you 1, and that's a 1 significant digit measurement, and your errors can be quite off with that. Okay, pretty sure this is all animated through, so yeah, we'll go through the calculation. Oh, I didn't, but all right, you know what, let's go through this. So position number 2 is at 27, I think. Yep, 27 meters, and D1 is at 1.0 meters. In fact, this would be at 27.0 meters. Why is it 0.0? It's because it's going right through 27. All right, it's not 27.1 or 20. Yeah, 20. It's going through 27.0. All right, so that's how we add another significant figure in there. All right, just by carefully observing where it passes through on the graph paper itself. And then T2 would be at 11 seconds, and T1 would be at 4.0 seconds. Should also add as a reminder that if this is a problem where you need to show your work, then make sure you state your givens. All right, so for your T1, your T2, your D1, and your D2. There you go. You got your givens. Your require is instantaneous velocity. The formula, sub the values in, and you can calculate it out, which I believe it works out to 3.7 meters per second. And oh, see, I just answered ahead of time. As mentioned earlier, Adrienne is 14 meters ahead, and Bobby would be 27 subtract 14, which would be 23. Okay, so that's how we solve this visually or graphically on a piece of paper. Now let's back this up with the mathematics. All right. Again, when you're solving these problems over here, you need to set a frame of reference. Does it really matter which one you set as a frame of reference? As long as you describe everything in their proper directions, it really doesn't matter, all right? But in this case over here, we'll just say that the first player is our frame of reference, all right? So we're going to use Adrienne as our frame of reference. She's the one who's moving forwards, and she will also be the starting point of this activity, all right? So now the Adrienne will have a position of 0, an initial velocity of 0, and an acceleration of positive 0.5 meters per second squared, as she is the one who's moving in the forwards direction. As for Bobby, on the other hand, Bobby is initially starting at 37 meters, and as he's moving opposite in the direction of Adrienne, that's why there's a minus sign. All right, so these are our givens over here. And yes, you could expand it out beyond here. For example, when I was mentioning to you audibly, I also mentioned that, what was it? dA initially was equal to 0 meters. And for VB, you have your A of Bobby, and that was equal to 0 meters per second squared. So you could add these 2 points if you need to as well. All right. I suppose next is, well, how do you exactly deal with this value here and this value here? Okay. Now, as for Adrienne, the third kinematic equation is probably most useful to solve towards solving her problems, which is delta D is equal to VI delta T plus 1/2 A delta T squared. And with this delta D over here, just remember that delta D means your displacement or your change in position. In other words, dF subtract di. So if you take the di and you bring it over, then you can figure out the final position of any given object as long as you know its initial conditions of where it started, plus its initial velocity, plus its rate of uniform acceleration. All right. So that's how we take the third kinematic equation and just slightly manipulate it so that it's relevant towards this problem over here. Okay, now we can sub in everything that we need for each of the players. So for example, for Adrienne, di goes to 0, vi goes to 0, and it has a value for uniform acceleration, and it simplifies down to that. As for Bobby, you could use Bobby with the same formula. What do we know? Well, we know that he started off at positive 37 meters in front of our frame of reference. He's moving back at negative 3.1 meters per second, and he is not accelerating. So that term goes to 0. And that's why we get something like this. And what do you do when you have 2 equations with 2 unknowns? You got it. Sub and solve. And that's what we'll do next. All right. For the first part, it's how long will they bump into each other? So we're trying to solve for time. So we want our displacements to equate to each other. All right. So we're just going to equate the 2 equations together for where will they share the same exact position. Sub everything in, expand, collect like terms, and over here you'll notice that time is quadratic and linear on this equation over here. So once you see that there's quadratic and linear, you know what to use, the good old quadratic equation. And before we get there, we need to convert it into standard form. So we want to start from the highest degree, which is anything that's quadratic, followed by the next term, which is linear, which will be positive 3.1 when you bring it over, and 37 when you bring it over, it will become negative 37, which will be our constant. Okay, we sub everything into our quadratic formula, crunch all the numbers out, and we'll notice that we end up with 2 terms, or not 2 terms, 2 solutions over here. All right. Now we know that the negative time doesn't make any sense, and that's why we'll drop it out, and we're left with our positive time, which is the only thing that logically makes sense. And I'll back up this this thing afterwards, all right, of why there's a minus time here. Okay, so we know that they're going to bump into each other at 7.454 seconds. And for the next part, how fast was the accelerating player going? Well, we want to find out how fast they're going at the 7.4 second meter mark. So we could use the formula of final velocity is equal to initial velocity plus rate of acceleration. As for Adrienne, Adrienne was initially traveling at 0 meters per second. So with a uniform acceleration of 0.5 meters per second squared, multiplied by 7.454 seconds, half of 7.4 is 3 and change. There you go. Okay, 3 and change, so 3.7 meters per second, and we've answered the second question. As for the third one, well, we can sub the 7.454 back into this equation over here to find out the position relative to Adrienne, And as for Bobby, we just need to take the absolute value of this, all right, because we want to figure out how far he's traveled. Well, 3.1 meters per second times 7.4 will tell us how far he has physically traveled. And that's about it for this problem over here. All right. Before we finish off, just two things to talk about. First off, why this minus sign over here? And it's partly due to the nature of how we're solving these problems. All right. You got to keep in mind that Adrienne, even though she was moving like this from time of reference of 0, her movement and her motion is all modeled based upon something that's quadratic, or in a quadratic function. Right. As you can see, her function is quadratic. And that's why there's going to be this left wing in the quadratic curve. Not that we need to factor that in, because Adrienne was not accelerating backwards, but that does exist. All right. And part 2 is that we only calculated out this picture over here. But again, Bobby's formula was also modeled based upon a 4-quadrant. What do you call these things? I forgot. Anyways, page. All right, so it's 4. I'll figure it out at the end. All right, and it's because it's based upon this. He also has this part over here. All right, so yes, based upon the modeling of this Euclidean plane, that's what I was thinking of. Okay, you'll notice that there's 2 points of intercept. One at 7.454 seconds, and another one that happens over here just simply because of the mathematics. All right, so that's where it came from. I don't want to ignore the minus sign, just tell you, just pretend it doesn't exist. It's because of this very reason. Okay. Another thing is that if you need to save some time, I know that by grade 12 you've beaten this thing quite a bit, or you've used it for probably about 3 years by now. All right, so yes, there is a little hack where you can use your calculator in solving it, and I do have a YouTube video describing this, but here's a little preview, and let me just add some things on top. All right, which calculators can do this? As long as you spend a little bit more money on your calculator, it will work. Often when you go to the grocery store or even Staples or whatnot, you'll see various calculators all on the wall, and often you'll see the same brand where there's a cheaper model and a more expensive model. The only calculator that can do this kind of stuff up here is the more expensive model. All right, so if there's one that's let's say $15 and another one's $20, it's the one that's $20 that has this neat little feature. All right, and it doesn't matter which brand you're talking about, Casio, Sharp, or anything else. One thing I do want to let you know is that at least Casio has their nomenclature set up. All right, in other words, their naming system makes sense. If you get the FX300 series, so FX300 something something, unfortunately that's a cheaper model and it'll never have this feature. It's only the 991 series that have this added feature where it can solve quadratic problems. It can also solve linear systems equations when 2 equations will bump into each other. It can do that as well. It can also do it in 3-dimensional space. So if you're continuing on in the world of math and sciences, you probably want to spend that $5 extra, or get the higher model when it's on sale in August. In any case, thanks for joining me. I'll catch you in the next episode. Bye now.